This is me, at 5 years old, just days after a series of tornadoes hit Smithville, Mississippi, just 15 miles from my mom's hometown. I may not have fully understood the events at the time, but watching a tornado literally level a small town of 882 people permanently changed my outlook on life. This profound moment sparked what is now a roaring fire inside me to help others in any way I can. I have dedicated my academic career to physics, and I'm committed to using scientific discoveries to help solve society's greatest challenges. So last summer, I was lucky enough to work at the National Center for Physical Acoustics at the University of Mississippi with Dr. Roger Waxler. Surprising to a young man from Manhattan, Mississippi has the most tornadoes out of any other state, including Tornado Alley states such as Texas and Oklahoma. Dr. Waxler's team specialized in using sound to detect loud, natural phenomena like earthquakes and man-made phenomena like nuclear explosions. More recently, however, the team has shifted the research towards understanding if acoustic technology can be used to track tornadoes. This could not be more relevant to modern society. According to the US government, over 1,000 tornadoes are reported in this country every year. And as many of you can probably remember, just 3 months ago, in December, a horrific swarm of tornadoes hit Kentucky, killing 80 people and causing almost $4 billion in damage. The victims reported that they were given only 20 minutes of warning time, which is 9 minutes more than the national average of just 11 minutes. Imagine if I told you that 11 minutes from now, everything you know, your house, your car, all your possessions, could just be gone with the wind in less time than it takes to listen to this TED Talk. Well, we can't stop a tornado once it forms. We can figure out where it is and where it's going, and warn people to take shelter or get out of the way before it's too late. But before I tell you about this exciting tornado research, let's review the science of sound. So what is sound exactly? Well, it's a vibration that travels through air, water, or other substances as an acoustical wave that causes pressure that repeats in a curvy pattern over a defined amount of time. Frequency is a physical phenomenon of sound, whereas pitch is a perceived phenomenon of sound. In other words, this means that we perceive frequencies as various pitches. High-pitched sounds have high frequencies, and low-pitched sounds have low frequencies. But to get some perspective, let's take a listen to some frequencies here. We humans can't hear frequencies over 20,000 hertz, called ultrasound, but some animals, like bottlenose dolphins, can. On the other hand, we call audible sound frequencies between 20 hertz and 20,000 hertz, and frequencies 20 hertz and below are called infrasound. While not particularly useful to humans, some animals like elephants use infrasound for long-range communication. Elephants and tornadoes, they're not so different, and not just that you don't want one on top of you. While you may not be able to hear this frequency right now, you could feel the vibrations. Tornadoes are low to the ground, and this makes it nearly impossible to track them with weather radar. Binoculars are only good on clear, sunny days, and useless after sunset. These methods rely on one sense, our sight. But ponder this. What if we used our ability to hear tornadoes? This seems simple, but humans can only hear tornadoes just before it's too late. This isn't good enough. So that led Dr. Waxler's team towards looking at infrasound, which again are frequencies below human hearing, to track tornadoes. And there are two key characteristics of infrasound that make it really awesome for this task. First of all, infrasound can travel much greater distances than audible frequencies, dozens or hundreds of miles even. And second, physical barriers don't seem to interfere with infrasound, allowing it to travel through walls, buildings, and even mountains. Fortunately for us, engineers have developed custom sensors that correspond a change in pressure in the atmosphere, which is sound, with a change in voltage on our sensors, which we can read. Now suppose we were to go out into a field and pick up some of the available infrasounds. What would it look like? Well, here's the thing. This orange line here is messy. And it's hard to get any useful information out of this, which is why scientists have come up with data filters that we can use to remove unwanted frequencies that muddy the data. Now this is impressive, but it lacks a critical piece of information. Can anyone guess what that is? Direction. Tornado warnings aren't helpful if it's just a binary, is there a tornado, yes or no. We need to understand where the tornado's been, where it is, and where it's going. And to do this, one sensor just isn't going to cut it anymore. We're going to need an array of sensors. So now suppose that we replace this sensor with an array of 3 sensors out on a field. We could have infrasound come from a known direction. As you can see, each of these sensors is in a different location and picks up the infrasound signal at a different time. In this example, the sound first hits sensor 1, followed by sensor 2, and then sensor 3. If you have enough of these sensors, sound from any direction will lead to one unique set of time delays. And what's great about this is that we can reverse engineer these time delays and solve for the direction. This process is called beamforming. And the power of beamforming increases dramatically if we add more arrays to the system. Each of these arrays can draw a line towards the source of the sounds, and these lines intersect at a point. This means that we can triangulate the location of the tornado. But this is only helpful if we can find the tornado's location in real time. If we break up the acoustic data into small chunks and repeat this process over short time intervals, a computer can track the tornado's position and velocity and predict where it's going. This is critical to warning people about the danger of tornadoes and how to stay safe during these natural disasters. This technology is cutting edge, but it's still got a long ways to go. Right now, these sensors are bulky, stationary, and expensive. Just one of these arrays can cost more than $12,000, and if you want an entire system of arrays, that can easily be north of $50,000. Right now, to set out one array of sensors, we need an entire football field of space. Not to mention that to collect data for these, we need to drive up to the sensors, download the data on a flash drive, drive back to the lab, and analyze it there. For obvious safety reasons, we can't do this during a tornado, which means that right now, the best we can do is analyze this data after the fact, once the tornado is long gone. But we can do better than this. Instead, I propose that we use mobile phones to track tornadoes. Mobile phones are, of course, light, mobile, and absolutely everywhere. And the best part is, the infrastructure is already there. Most people already have cell phones. More phones means more data, which means that we can give people faster and more accurate warnings. And this technology may be here sooner than you think. With a little more research and development, we can give people faster warnings that give them more time to protect their property and, more importantly, save lives. Thank you.